Morning, everyone. And we've got that recording. Got it. Okay. Good morning, everyone. It's so nice to interact and engage with you again here in Cotton and Coffee. As introduced, I'm Vikki Martin, and I really love to talk about fiber quality. So one of the things I intend to do today is to give you a little bit of a textile 101 as to why fiber quality is important, how it impacts yarn quality, how it therefore impacts fabric quality. And then I'm going to sum up my presentation today telling you some of the research activities that we have to try to advance fiber quality for U.S. cotton. So this presentation might be for you if you have ever asked yourself, why are some qualities discounted severely? Why are textile mills so picky about micronair? What does color matter? I mean, don't they just bleach and dye it anyway? Hopefully after about the next 20 minutes, you'll have a much better understanding as to why textile mills can be so picky about our fiber quality. I want to start with some fundamentals about how micronair is measured. It is a simple measure of air permeability of the compressed cotton fibers. And when we are doing a micronair measurement on the high volume instrument, such as in classing, we're actually getting an indirect measure of both the fiber fineness, how thick or thin that fiber is, and the fiber maturity, how much cellulose actually developed and was placed in that fiber during growth. Now, the challenge with micronair, which makes it a little problematic for us, is that we can neither tell the individual fineness or the maturity when we look at a specific micronair value. In terms of how the measurement is done, it's based on the concept of a fluid flow through particles. So when you've got large particles that are less packed together, air moves more quickly. When you've got smaller particles that are packed closely together, the air moves slower. So in this case, when we've got coarser, more mature, larger cotton fibers, that air is going to move fairly fast through there, and we get a high airflow and therefore a high micronair value. When we've got finer, smaller cotton fibers or maybe immature fibers that are packed closer together, that air is going to be harder to flow through there. And when it does, we get a lower micronair value. The way that I want to define and explain this to you further about the challenges that we have with working and dealing with micronair is that, again, we don't know if we are getting a mature fiber or an immature fiber, or if we're getting a fine fiber, a thin fiber, or a coarser fiber when we look at a specific micronair measurement. And I'm trying to demonstrate this with the graphic on the screen right now. Up at the top, we have two different micronairs. We're looking at a 3.5 and a 4.5. On the left side, we're looking at different maturity levels. The higher the maturity value, the better. That means it's a more mature fiber. And then within the boxes, we're looking at different fineness levels. The lower the fineness value, the better. That means it's a smaller fiber, and we would like to have smaller fibers because that gives us an opportunity to make smaller yarns, which gives us some competitive advantage when we're competing against polyesters and the rayons, which are very thin fibers out there. So when we look at the 3.5 mic in that upper left box, that's a high maturity and it is a good fineness. That's a good fiber to be working with. However, what we don't know is that we may have the situation in the lower left box where we've got a lower maturity and a coarser fiber. And you can see that large open white space. That represents the fact that there's not much maturity in this fiber and it's going to be harder to process. And that's not the version of the 3.5 that we want. Same situation when we're looking at the 4.5 and the upper boxes. That's good. That's a decent fineness. It's a good maturity, but that lower right box, that's kind of a worst case situation. That's an immature fiber that's very coarse. And this is why we have the challenges with micronair and understanding micronair values. Now, one of the things that we get with this is that, the upper situation is good, the lower situation is not. And this is why micronairs of 3.5 and 4.5 fall in that base price point. When we think in terms of the premiums and discounts that classically, are going around the price of cotton, the best micronair is going to completely depend on the product that is being made and the spinning system that's being used to create the yarn. But in general, we tend to consider that base areas of 3.5 to 3.6 and 4.3 to 4.9 to be where we think what we know what we're getting. We think we're getting a mature fiber. We think we're getting a fineness that we can work with, but there's some uncertainty associated with that. If you get micronaires below 3.4, you're going to assume that that's probably because it is an immature fiber. And if you get a micronaire above 5, you're probably going to assume that's a very coarse or very thick fiber. And those two ends are not necessarily going to be the situation that you want for a lot of products, which is why we tend to consider the sweet spot that 3.7 to 4.2. And that's because at this range in micronaire, classically, we can believe and have true with the assumption that we're getting a sufficient maturity in that cotton, but we've also got a good fineness that we can work with. And these cottons tend to fall into an optimum range for spinning and processing. Why are fineness and maturity important properties? You know, we've got that micronaire measurement, but we're really thinking about the fineness and the maturity of the fiber instead. That's because not only does it impact the yarn quality, it ultimately can determine what size yarn is physically possible to make. If you're working with a very coarse fiber, a very super high micronaire fiber, then that is going to restrict the yarn size. You cannot make a super thin yarn with a fat cotton fiber. It's just not physically possible. In addition to that, both of these properties will impact the amount of processing waste. They're also going to impact spinning performance. And I will mention spinning performance and the concept of ends down several times during this talk. And ends down is essentially whereas we're spinning that yarn, the yarn physically breaks going into the package. And that stops the spinning process for that particular cone of yarn. And the end has to be reconnected. And that's slowing down our efficiency. I'm going to cover NEPs in a few more slides, but just understand that both the fineness and the maturity play a role on yarn and fabric quality, and even have an impact on the appearance of dyed fabric. So for several of the fiber properties today, I'm going to take you through what's important both from the yarn as well as the fabric perspective. And so here we're looking at some key impacts on yarn and yarn quality. The hairiness is going to be the surface characteristics of that yarn. It'll play a role in how soft the yarn and how soft the fabric feels, but it also can lead to an impact on how the surface of the fabric looks, which may or may not be pleasing. The strength of yarn is going to directly play into the strength of the fabric. Can you take that yarn and can you beat it up and make a woven fabric from it? Imperfections are going to be thick and thin places and unevenness in the yarn that can create a physical disruption in the look of the fabric, which may not be desired or can contribute to weak spots in a fabric. And then, of course, that spinning efficiency again. Can you efficiently produce this yarn without a lot of problems and ends down? And you'll see that micronaire plays a critical role in all aspects of yarn quality and spinning performance. When we get to fabric, we look at things such as dyeability. How easily does it dye that fabric? Appearance can be different from color. Appearance can be the surface effects and how that fabric looks. Strength, of course, is very important in fabric in terms of how a garment is going to perform. And then we can have an attribute known as pilling, where we get entanglements of fibers on the surface of the fabric, and that's attributed to specific fiber qualities. In the case of the fabric issues, you'll see that micronaire is important for 3 out of the 4 categories. I want to take a few moments to talk to you about NEPs. NEPs, I mentioned, is a challenge that we have in processing. It is an entanglement of predominantly immature fiber. We can have what is known as biological NEPs, where that immature fiber has occurred naturally in the ball of cotton. Or more commonly, we have what's known as mechanical NEPs. And this is where we have predominantly lower maturity fibers that every time we engage and interact with that fiber mechanically, we are potentially generating NEPs. The harvesting technique that we use, the amount of cleaning that we do in ginning, and even all the cleaning that we do in the early stages of fiber processing can contribute to the formation of mechanical NEPs. Neps are very difficult to remove from cotton fiber. And when they get incorporated in the yarn, they tend to remain on the surface of that yarn. And they are going to be essential for a lot of yarn defects and then ultimately fabric defects as well. Because they're predominantly immature fibers, they do not dye the same as the rest of the cotton in a fabric. And so the photo on the left there is a photo of a nep, and it is on the surface of that yarn, and therefore it ends up on the surface of that fabric. And when we dye that fabric, that nep is not going to take the color, it's not going to take the dye effectively, and we get a defect known as white specks. Another challenge that we can have with micronair is an issue known as barré. And this happens when you're mixing together yarns of different micronair. In this case, we've intentionally created it with yarns of different micronair values. When it happens in the real world, it's a mix of different micronairs that results in unintentional banding in that fabric. Barré can be caused by not controlling any property that can impact how we perceive color. So it's not just the micronair, it is also the color attributes, that RD, the reflectance value of cotton, and the plus B. And so this is why color can be very important. Even though we're going to bleach and dye it, how we bleach and dye it is going to be influenced by the initial color of that cotton. Other things that can contribute to barré can be the textile mill's fault. It has nothing to do with the fiber quality. It's that they didn't set things up correctly in yarn or in their knitting parameters, or they actually made the mistake of mixing together yarns of different properties. And I want to demonstrate that here for the next couple of photos. What I'm showing in these photos is where we had yarns of 3,4 mic and yarns of 5,0 micronair. We knit them together in bands, and then we dyed that fabric. And hopefully on the screen, you can actually see physical bandings with the lighter and the darker alternating there. This is a result of not only the maturity differences in that fiber, but more critically, a result of the differences in the fineness between those different fibers, because a thinner fiber versus a fatter fiber, they have a different surface reflection. And so this is in part how we are perceiving the color, not necessarily how much dye is actually on that fabric. We take the micronair a little closer, looking at 3/8 versus 4/6. You can still see that banding. It's not as drastic, but it's certainly still there. And then we take it into kind of the sweet spot range. Those bands are still present. They're much harder to see. A well-trained eye can actually see that. If we were intimately blending the 3/8 and the 4/2, we probably wouldn't have a problem. But that's why these values play a role. The maturity and the fineness have a critical impact. And this is why we try so hard to control these properties in textile processing. Some of the other things that contribute to barrés, I pointed out, is the color. And one of the challenges that we have with cotton color is that, essentially a lot of things can change the color of cotton. Once that bowl is open, anything that the cotton is exposed to, whether the weather is normal or severe, the contamination we get through the environment with the soil, the insects, even time will change that color. And I'll come back to that time concern in a moment. The reason that we view color importantly is that however a textile mill is specifying what color they want, that's their concept of what they consider their normal grade or desired color. And then any variation from that becomes a problem from them. And this is why we do officially have a color grade. And with any type of grade, we then have a property that we have the ability to control. The challenge is that comment about the change with time. It's the only fiber property that can change and does change with time. We know that both the RD and the plus B will change with time. Over the first 6 months, there's going to be subtle changes in both values due to the natural activity of the microflora that's present on that cotton fiber. After that is where things get interesting. After 6 months, there can continue to be changes, but those changes aren't necessarily consistent. And we can see bells that remain very stable for color over time, and we can have bells that actually can change rather significantly in as short as 6 to 8 months, often shifting a color grade. And that can be a problem in terms of management in a textile mill. Color grade, again, it's going to impact how we dye the fabric. It's going to determine the level of bleaching and dyeing that's going to be needed to get the ultimate appearance of the fabric. And I'll also point out that trash grade also has an impact on the ability to dye a fabric and the appearance of the fabric as well. Trash grade is also important when we get to spinning efficiency. Having trash that we can't remove in the early processes of cleaning and carding, that is going to contribute to a higher risk of ends down. And just as one example, there's some evidence that shows that you can have an end down increase of more than 50% for every 1% increase in bark content in your laydown. So why are bark and grass a problem? Well, bark and grass just happen to mimic the behavior of a cotton fiber in processing. They are very difficult to remove in cleaning. They easily become a part of a yarn. They behave the same as the fiber when they're going through the spinning system. If they're in the yarn, then that's a yarn defect. It's a greater opportunity for that yarn to want to break or to increase those ends down, as I've mentioned. If it survives the yarn process and it's in the yarn as a defect, then that's a higher opportunity for a defect in the fabric and damage in the fabric itself. Since we're talking about all the fun extraneous matter, I thought I'd go ahead and throw in the C-code fragments as well. They are additionally hard to remove from cleaning. They also cause similar defects, breakage, and ends down. And additionally, C-code fragments are very interesting because they can mimic a situation that we get when we are unfortunately dealing with sticky cotton in the mill. And I'll explain that further in a minute. So there are occasions when mills actually have higher levels of C-code fragments that think that they have sticky cotton, but they don't have sticky cotton. They just have a C-code fragment issue. The upper left photo is an example of when bark gets entangled and has become a physical part of that yarn. So you can see that it behaved just like the cotton fiber did. And the lower photo is showing the buildup of bark and the carding flats during the processing. And this now becomes an issue that the textile mill has to take time to try to clean out from their spinning and cleaning equipment. These photos represent C-code fragments, and unfortunately that's not the clearest photo in the top left. It's a very nice old historical photo, but those large clumps you see, those are C-code fragments entangled in that yarn. Absolutely going to be a point that it's going to break. Surprised it made it into the yarn in that form. The real issue that we have with C-code fragments is where you see it building up here on the roller and the grooves and spinning. Those C-code fragments can become embedded in the roller and in the grooves. And as the spinning occurs, they're getting crushed and they're releasing little bits of cottonseed oil, which creates a sticky surface. But in addition to that, these fragments, they're rough and they actually snag cotton fibers. So cotton fiber will begin to collect more and more over time on these parts of the equipment, and they're going to have to clean them more often, which is going to slow down our efficiency in operation. So what haven't we covered that shows up in these slides? We know length and strength are important, but those aren't problematic for US cotton. We have beautiful length and strength. But one of the things that does show up consistently in the fabric area is going to be length uniformity. That's going to have an impact on the appearance of the fabric. It will certainly have an impact on the strength of the fabric. Length uniformity can play a critical role in whether or not we have surface peeling. If we get additional fibers that are sticking up and they're more prone to entangle with each other because we have a lower length uniformity, then that can contribute to peeling issues in fabrics. Length uniformity is very critical across all aspects of yarn processing. It plays roles again in the hairiness, the strength, the imperfections that we get, as well as the spinning efficiency. Just to give an example of the impact of length uniformity on spinning efficiency, I can tell you that in 2018, we saw a drop in length uniformity in the Southeast and the Mid-South crop compared to historical averages. We had a couple of our US mills that had gotten used to enjoying very high length uniformity from the cottons that they typically source, that weren't paying quite as much attention to their contracts and ended up with some lower length uniformity than they were used to working with. And this actually contributed a significant issue in their efficiency in processing. Their typical number of ends down was about 350 ends down out of 1,000 spindle hours. They still were struggling with twice the amount of ends down, even after they slowed down their spinning systems by 10%. So length uniformity can have a real critical impact on spinning efficiency. But other than that, length uniformity plays a very important role in yarn size, particularly in ring spinning. Ring spinning is the most predominant spinning that occurs globally. And that length uniformity is ultimately going to help determine how small of a yarn diameter you can create. I spent a lot of time talking to you about micronair, how that's important, but it's really fineness and maturity that we're really focused on. Color can be an interesting challenge for us. Extraneous matter does cause issues in textile processing, and that length uniformity is important. So what are we doing at Cotton Incorporated relevant to these properties? Well, historically, for those extraneous matter issues, the bark and the seed coat fragments, that's research work that's taken place primarily in our ag and environmental division. So Dr. Ed Barnes is the one that I would go to whenever I've got challenges with bark and seed coat fragments in particular. In fiber competition, we're currently doing research on two of the more critical fiber quality properties in our Fiber of the Future program. We're focused on improving length uniformity measurements for cotton breeders, and we're working on fiber fineness. The reason that again, we're focused on length uniformity and also on fiber fineness is that both of these play a critical role in yarn processing. They can play a very critical role in the size yarn that we want to produce. And we are trying to make cotton more competitive against the rayons and the polyesters out there and move us into market categories. And one way that we can do that is if we can fine tune our uniformity and our fineness, we have a greater opportunity for greater market potential. The reason that we honed in on length uniformity as a need is that we track long-term fiber quality trends. We've seen significant improvements in length and strength over time, but length uniformity is a property that has been on the decline. A half a unit difference in length uniformity can be meaningful depending on what fiber length you're working with and what you're trying to produce. The way that we've tackled trying to improve length uniformity is to get a better measurement out of the high volume instrument for breeder testing. I'm not talking about any type of change in testing that would contribute to the classing and the grading of cotton, but specifically better data to go to the cotton breeders out there. For length uniformity, what we really want them to improve is the actual length distribution. And there are ways of doing that on other instruments, but they're very slow and very expensive and aren't utilized as much. So we focus specifically on trying to get a length distribution out of the HVI. And we were able to do it. We're in the process of making it commercially available. We have a private breeder that is working with us, commercial private breeder this year and next year. And you see his samples on the screen. The graphic on the left is the classic HVI length measurements, and the graphic on the right are the new measurements that we are capable of getting out of the HVI system today. And what I hope you can see, the difference here is that we are seeing a much better spread between these cotton samples that we wouldn't have seen throughout the classic HVI properties. And this better dispersion of the data allows us to really pick and choose which lines we want to move forward that have the real potential to improve length uniformity in the future. In fiber fineness, this is all about planting elite genetic materials in multiple locations and doing tons and tons and tons of measurements. We're trying to build a database of genetic information. We're doing testing with the Advanced Fiber Information System, which does give us a measure of fineness and maturity. But if we really want to focus on fiber fineness and maturity, the best way to do that is the reference technique, which is that fiber cross section that you see in the lower photo. Fiber cross sections are very problematic. They're almost an art form to do nowadays. They're hard to embed. It's hard to get clean slices. It's very difficult to do. So it is not a reliable, consistent measurement to use in a breeding program today, which is why we are putting research time and effort into improving the cross-section techniques. We're moving this forward to make it an easier bedding mechanism to do easier cross sections, and are trying to make this a rapid test method that can be utilized better going forward. Between both sources, we're getting tons of information on fiber fineness, which is our goal for triggering, with the hopes that in a few more years, we will have a large enough database of genetic information that quite potentially the breeders could find a genetic linkage that will turn a trigger for improving the fineness in upland cotton. And that's one of our long-term goals within fiber of the future. I have covered a lot of information today. Hopefully you have a little bit better understanding about why fiber quality is important. It's about, we get kind of fussy sometimes when we're looking for our fiber quality. Everyone gets frustrated when we have challenges that lead to excess extraneous matter. That micronair and color are important but challenging properties at a textile mill, and that we continue to try to do research work on fiber quality to push fiber quality as high as we can get it, to continue to make cotton more competitive against the rayons and the synthetics, which are cut to any length they want to be. They're all the same length. They think they're the perfect fibers, but we've got a lot of advantages, and I think we can do more to compete against them. That is it for my presentation this morning, and I would love the opportunity to engage with you for a while with some questions.